Okay, so hello everyone. In this video, we'll be showing the question number 1406, which is the stone game part 3. It is marked hard, but the question is very easy to understand as well. The question is very moderate to approach as well. Constraints are to be considered, and we'll first understand the question, understand the examples, and then move to the approach. Okay, so yep, let's first understand the question, and then later we will proceed to examples. Okay, so Alice and Bob continue the games with the piles of stone. There are several stones arranged in a row, okay, which means that it is an array, and each stone has an associated value, which is an integer given in an array stone value. Okay. Alice and Bob take turns, with Alice starting first. First, this is the most important thing, that Alice is the one who is starting the game. On each player's turn, they can take one, two, or three stones from the first remaining stones in the array. Suppose there are, okay, just a minute, guys. These are the stones. These are the stones. So this guy, the one player which is playing, has three options that he can pick one, or he can pick two, or he can pick three. He can pick these first, these two, and these three. But he can only pick from the starting. He can only pick from the starting. Okay. Each The score of each player is the sum of the values of the stones taken. Okay. If someone decides to pick just this stone, then his score will be his current score plus the value of this stone. If we chose to pick these two, his score will be the sum of value of this stone and this stone. Okay. The objective of the game is to end with the highest score. Okay. Everyone wants to win, right? And the winner is the player with the highest score. And there could be a tie. Okay. The game will continue until the all stones have been taken. And this is the most important thing, that assume Alice and Bob play optimal. What does this mean? What does this mean is that whatever elements are remaining, they pick them in the most optimal way. They pick them in most optimal or efficient way. Why would they do that? So that the scores are maximized. Okay. So what they will do is, from whatever the options are left, they will try to pick them in the most efficient way so that their scores can be maximized. How can they do that? Is that from the remaining elements, they have three choices: that the first one element, first two elements, or the first three elements. Whatever element they pick, their values will be added to their current score. Okay. Let's look at the constraints. The constraints state that this value or length of the stone value can be 1 till 5 into 10 power 4, which means that the number of stones can be 1 or till 5 into 10 power 4. So the possibility of using n square is nearly ended, because n square would result in the squaring of this number, which would be greater than 10 power 8. And moving beyond 10 power 8 is DLE, and the stone values can be minus 1000 till 1000. Let's take one example. Suppose it is 1, 2, 3, and minus 9. Okay. Suppose we have three options. We will tally and move forward. Okay. Suppose these are the stone elements, and we're given that Alice starts first. Okay. So when Alice starts first, she has three options, which is just to take the first stone, or to take the first two stones, or to take the first three stones. So there are three possibilities. And if we want to play optimally, if you are playing a game and you want to play optimally, what you will do is, we will check out all the possibilities that which and think that which possibility gives me the maximum result. Okay, so suppose Alice picks just one element, which is 1. Then Bob is left with 3 elements, which is 2, 3, and -9. If Alice picks this one, then Bob has 3 elements, which is 2, 3, and 9. Okay, which is, let's write that down over here. 2, 3, and -9. Okay, and from that Bob decides to take one value, because at this point also Bob has 3 options, which is to pick one element or 2 element or 3 element. As a result, what will happen that at each point everyone has 3 possibilities, so they will explore the 3 possibilities. Okay, here Alice had 3 options. It is to pick one element, pick 2 elements, or pick 3 elements. Later, after each possibility, Bob is also offered 3 possibilities to take 1, 2, or 3. As we do this efficiently, we find out that Alice reaches a particular score and Bob reaches the particular score. Suppose what you get is Alice score is X and Bob's score is Y. If X is greater than Y, we return Alice. If X less than equal to Y, we return Bob. Okay. But to make it easier, what we can do is at each juncture is nothing but at each possibility, at this particular, sorry, at each level, here, 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 we, at each juncture, we just check what is the difference, x minus y. And if at the end x is greater than y, we can say that okay, L is 1. If x is less than equal to y, we can say that Bob is 1. So our main key is to maintain the difference at each junction. And since we are said that Alice and Bob and play optimally, so we want to obtain maximum score. So the one field, one choice that yields maximum result, we will choose that. Okay, which is maximum, take 1, take 2, take 3. Okay, that is one of the key things which we do. And how do we maintain the difference? Suppose I pick x elements, and now okay, if I pick x elements, then my current score will become sum of x elements. Now it will be the turn of next guy, and what I want is to maximize the difference score or maximize difference. So my pick, which is nothing but what I have picked, minus what the other guy would pick, or you can in simple terms say others score. And what we want is that we maximize it. We want to maximize it. Okay, so that our score is maximized. Suppose let's say Alice is x and Bob is y. Okay. Okay, so Alice is x and Bob is y. So at this point, Alice will think that okay, what is my pick and what is the Bob's optimal choice, Bob's optimal score. Okay. At this point, Bob will think that what is my pick and Alice's optimal score after picking his choices. So you might have found that this is later this is later passed on to here. So if we Bob want to win, his score should be greater than Alice's pick. So we need to maximize this as well. Okay. Here also Alice's score is used. Also, so as a result, Alice would want that this difference is minimized. So everyone will be trying to maximize the score. Okay. So since you can say that this is a recurring problem, how? Because at each junction there are three more possibilities, and from those three possibilities, more three possibilities generated. So a tree is created. So we can think that three possibilities. In this, each tree will create three more, so it will create 9 possibilities, 27 possibilities. Okay. And what we'll try to do is we will pick three options, and what we'll do is subtract other guys turns score, and we will select max score till when no elements are left. Okay, so let's move to the approach. Okay, so since we are creating a recursion function, we if we do not know what integer type, like what return type are we expecting, so we will get that along the way. Let's just first create an helper function, and while we are iterating, we'll be like, okay, currently I am at this position, currently at an I equals to 0. Now I have three options: 0, I plus 1, and I plus 2. And if we take I will be at I equals to 1. And from that I will have three options: I plus 1, I plus 2. So we need one variable which is I. It is of integer type, and we are iterating a vector. So it would be vector int and vector int and stone value. Okay, so as of now we require two parameters which are integer I and this vector array. And now we'll move to the input. So what we decided was until no more integer or like stones are left to pick. So if I is greater than or equal to stone value dot size, we can say that I have nothing more to offer, so we'll return 0. Okay, now at each junction we have three options to take 1, take 2, or take 3. Okay, what is our take 1 int? Take 1 is what you can say this current I, and now the difference of next guy's score, which will be helper I plus 1, because we have picked the I. He will start from I plus 1, and stone value. If we take 2, it will be sum of this current one and I plus 1, and now next guys will be helper. Since we have used 2, now he will start from I plus 2. Okay, if we take 3, it will be I, then I plus 1, and then I plus 2. Now difference, let's put it this way. Now the difference with next guy score, now he will start from I plus 3 and will pass the stone value. Okay, now what we will do is we will return the maximum score Alice could get, since she is the one starting after having three options, which is take 1, take 2, and take 3. Maximum parameter can take only 2. So what we'll do is first we will find the maximum of take 1 and max of take 2, take 3. Okay, So whatever will be the maximum of this, it will be then checked with this. Now let's try. It is an integer, returns integer, so this is the integer. So if helper 0, we're starting from the first element because we are told to start pick from the starting. If helper or greater than 0, which means the difference between Alice and Bob's score is greater than 0, we return Alice, else we return Bob. Let's check. Okay, now what will happen is, if suppose we reach the end, like if there are only one element is left and we try to access the next element as well, it will give us an runtime error that current number is not reachable. So what we can say is, we can give and check here only, if I plus 1 less than stone value dot size. Okay, then only this would do, this would be done. And here also, if I plus 2 less than stone value dot size. Okay, let's now what will happen is, if this statement is not being ran, then take 2 would not be initiated. So as a result, here it will give error. So what I'm thinking is, why not just initialize everything or declare them everything like beforehand only, if with integer mean, with the lowest value possible. If these equations are satisfied, they will get a particular value, right, which will be 110% greater than integer mean. Okay, so int take 2 equals to int mean, int take 3 equals to int mean. Okay, okay, okay. If it is a tie, we are supposed to return tie. Okay, now if let's just store this somewhere. If score is less than 0, it means that difference of Alice and Bob is less than 0, and as a result, score of Bob is more. So we return Bob in this case, else we return tie. Okay, let's try to submit this. This will not be submitted because its constraints are, it is an exponential time complexity question, and the number of length is so big, because you can see that at each point, at for each I, there are 3 possibilities, and as a result it will be 3 power I is nothing but the nums dot length. As a result, the time complexity will be 3 power n, where n is the length of stone array size. Okay, so we need to optimize it. How we can optimize it is that, suppose if this scenario has occurred before, we can use it. This is nothing but a DP, dynamic programming, because a same repetitive reoccurring trees are originated or generated, and we are recalculating it every time. So why not just create a DP? And how do we create a DP is, first we check how many number of variables are changing. In this case, only one variable is changing, so we need to create one DP. And what is changing? I is nothing but the index, and index is can be possible from 0 to n minus 1. So we will create an vector which will store the possible scores. We will name it DP, and its size will be stone value dot size, and we will declare it with integer mean. Why not -1? Because the values can be negative. What if all the values of stones were negative? Okay, stone value dot size int min, and it will be required in the function pair definition, right? And we need to pass that dp everywhere wherever we are calling, here, here, and here, and in the final call as well. If now we will check if dp of I not equals to integer min, what we do is just simply return dp of I. If this has not happened, it will move to this line of code. Then that time we need to store it in the dp of I. Okay, let's first run this. Okay, let's submit this. Okay, so our code is submitted, and its time complexity will be O of n, or you can say 3n, because only one variable is changing and three possibilities are there. Time complexity will be O of n square. One would be for the stack trace, and the second will be for dp of 1d vector. Okay, so I hope you guys understood as well how we are approaching and why we chose difference. Because after each peak, what we'll do is, just to maintain, we'll try to maximize our score, which is nothing but our score minus the next optimal possible score of the next guy, which will be obtained from the remaining array. Okay, so yep, if you have any doubt, do let me know, and thank you.